Hello YouTube and welcome back to my channel. Today on the bench I have the second supply from Tony, the one which had its fan board blown and it's missing its gate driver. So let's open it. From what I have seen in Tony's video, it seems like a MOSFET gave out, and looking at the working board from the first power supply, it is a P-channel MOSFET on the output to the fan. Why would that fail? I am not sure, because the fan that Tony tested the board with was working. It was the fan from the power supply I have fixed in the other video, the one with the not working PFC, uncooperative. So why did it give up? Well, it shouldn't. So maybe the MOSFET was already damaged. There we go. This is the board, and indeed, I told you I have noticed what seemed like a MOSFET failing in Tony's video. Come on, focus. Yep. You see? Isn't that a hole in it? Or is just paint? Paint. Sorry. Oh no, it's not a MOSFET. A poor SOT23 device. Come on, focus. We'll see it better under the microscope. Why on earth would that fail? Is this fan faulty and somehow damaged this board before Tony tested it with the working fan? I don't know, but we will test it. One nice feature about this power supply is that all the screws are the same. It makes working with it much easier. I'm hoping none of the modules have problems. They seem to be very crowded. What are these? Transistors? It has to have some transistors. I'm thinking maybe half bridge each of the modules, and probably resonant LLC. I don't know. But I hope I don't need to work on them. As I said, this board is missing its gate driver IC. Tony removed it to test it on the other supply and could very well have other issues. Also, the snubbing capacitor is missing, but Tony sent me new caps, so I have replacement for that. The jumper. Hey, Where did you fell from? I hate it when that happens. It did fell from this power supply because I cleaned this thing before I started. There are some jumpers here, but I don't know. Luckily, I have a working power supply. I can check. Do they have jumpers? Mm, I cannot see. Does this have a jumper? No. I hate it when this happens. But maybe it is from here. I remembered Tony sending me some high resolution photos with the other board, and indeed the jumper is here at the first two pins, and I have confirmed it looking back at my other video. Why did it fail? I have no idea, because it seems to sit tightly there now. Was this a problem for the power supply? I'm not sure. Is it deformed? Seems to be a bit, but I don't think that's a problem. Now, as I said in the other video, I did measure between pins 1 and 8 of the gate driver IC, and I found about 300 milliohms. Although that gate driver was new and it was already soldered on the board. If I measure now without the gate driver, will I see continuity between pins 1 and 8? No, no continuity. That means that the driver itself has connection inside between pins 1 and 8. I'll check that when I get the new driver ICs. I cannot remember if Tony tested this board or not, but as I remember, someone said that the auxiliary flyback supply of this power unit is a common failure point. So I need to check this flyback driver, and according to this data sheet, pins 2, 3, 7, and 8 are the source of the MOSFET, and pin 5 is the drain. So how do we test it? Well, with the diode function on the multimeter, we test the MOSFET inside, between the source and the drain. If it is okay, we should find a diode, the reverse diode. With the red test lead on the drain and the black on the source, we shouldn't see anything. And we don't. There was probably some capacitor charging, although it stopped on what? Almost a volt. And the reverse way, we should see the diode. Yep, there is some capacitor charging, but where is the diode? Where is my diode? There must be some diode. All MOSFETs have them. And as I said, 2, 3, 7, and 8 are the sources. And when the black leads is on the source of a N-channel MOSFET and the red lead is on the drain. No, it is the other way around, sorry. Sorry. This is where the diode should be. So this is that almost a volt. Kind of large. the forward direction, the MOSFET doesn't seem to be shorted, but I'm not sure about that direct voltage of the reverse diode. Luckily, Tony sent me some spare parts, including some of these flyback drivers, so I can test and be sure. So, red test lead to the source, black test leads to the drain. The reverse diode. Yep, 435 millivolts. This is what the diode should look like, not a volt. And the forward direction, meaning the red test lead to the drain and the black to the source, nothing. So, this is a suspect. Most likely needs to be changed. Thank you, Tony, for this. Is it something on the board that increases the diode's forward voltage? It can't be. Anything on the board that could influence the measurement should decrease that voltage, not increase it. So yeah, most likely this IC is gone. And of course the gate driver needs to be ordered. What else? You know what? I have prolonged this enough. When I'm dealing with the power supply, I always suspect main transistors. And these are the MOSFETs from the PFC, and this is the diode. You know, 20N60, 20 amps, 600 volts. Let's see, this is the gate, drain, 1.369, gate source, 0.9, drain source, let's see, not shorted, yeah, yep, drain to gate, source to gate. This must be some diode in the gate. And this is the reverse diode of the MOSFET. Yep, this one is good. The other MOSFET, gate to source, to drain, so sorry. Okay, gate to source, same, drain to source, open circuit, source to gate. Why am I saying source to gate? Because I'm putting the red lead to the source, and it's the reverse way, and I need to point that out. So yeah, the same, drain to source, drain to gate, sorry. This one is also good, and source to drain, the reverse diode. Yeah, the MOSFETs are good. Now the diode, the PFC diode, it is okay. Yes, it is okay. What else? The diode that straps the PFC, as I remember, this one here, and this is the direct way. Yep, 0.5 volts almost, and the reverse way should be nothing. Yes, it is. What about the current shunt resistor? I'm testing with this analyzer. It's some open source project here in Romania. It's called Miro 63, Miro 63. It is a treasure, trust me. It can test capacitors from a few picofarads to, I don't know, couple hundred millifarads. It can test the ESR. with very good precision. It can test small resistors with good precision down to 10 milliohms or something. It can test inductances, and it can test anything in the circuit, and that is awesome. And I have set it up to test small resistance because I want to test this shunt resistor. Yes, 47 milliohms. I have two of these devices and I love them both. What else can we test? I'm not sure, but I'm guessing the only problem with this board, beside the gate driver, which seemed to be faulty in Tony's video, is this guy. I just remember I didn't tested the fuses on the mains. This one is good. This one is good. Yeah, good news. Because these fuses are pretty expensive. Let's test some diodes on the board. It takes a short time. This is the diode that charges the capacitor, which turns on the MOSFET, which in itself powers the relay. Yep, it's not shorted. Testing it the other way around, it is not necessary. This is the reverse diode on the output of the gate driver. Yes, it seems to be fine. This is the diode, the backwards diode, the reverse diode on the relay coil, but we cannot test it with the diode function because the relay's coil resistance the coil resistance tricks us. But we can see if we have some, yes, 365 ohms. Seems right. What about this 1 ohm resistor? 10 ohms, sorry. It is okay. This diode rectifies the ground path of the auxiliary 12 volts supply. You know, the one that powers the PFC control IC, the gate driver, this comparator, and whatever else. Is it okay? Yes, it seems to be okay. Not sure what they felt they needed to rectify the ground path, not the plus side. But hey, it works, so. I knew those diodes couldn't fail, but still, you know me and my redundancy. And speaking of redundancy, you know what the fault was with the other board, so why not? This is pin number 4. Do I have 750Ks here? Just to be sure, right? Come on, you can do it. Yeah, we do. So, nothing else seems blown. What comes next? Well, I am thinking I put a new cap here in the snubbering network. I desoldered this flyback controller and I will measure its drain and source out of the circuit. And I can test when I put a new driver in its place, I can test that I have a working flyback auxiliary supply. But before that, we need to make sure the MOSFETs from the PFC are safe. And why? Because the gate driver is missing, and we need to make sure that the gates of the MOSFETs are not floating. That would most definitely cause a catastrophic failure on the MOSFETs, and they are not floating because, as you remember from the schematic, they have a 2.5K from gate to source each one, so they are safe without the gate driver itself. And this reverse diode makes sure they do not receive reverse biasing on the gate. So yeah, let's desolder this one first. This flyback IC doesn't seem to want to cooperate. It could be melted down on the board. I didn't want to risk damaging the pads, so I've used this mylar tape to protect the board, especially these caps and the smaller SMD parts. And I'll use my hotter station set up to 400 degrees and about 30% of air speed. Finally. I hate lead-free solder. I absolutely hate it. I know it's regulations and stuff, but hey, I get to hate it, right? Nothing seems to have been damaged. It is a multi-layer board, and it sucks the heat away quite fast. So let's see. This is the source, this is the drain. And in the direct way, we should see nothing, right? And we don't. The reverse way, hey, where's my diode? I don't have my diode here, why? Nothing. It can't be. It has to have a reverse diode. Solder wick. Get yourself as much solder wick as you can. You will use it like crazy, but Why do I dry the board with my hotter station since alcohol IPA is harmless? Well, it's a good practice, I think. Why not? Did we do any damage here on the pads? No. Everything seems okay. Even that tiny resistor, right? Why didn't I get my reverse diode on the driver? It couldn't have been, it couldn't have been from desoldering it. I didn't heat it up that much. Certainly not enough to damage the diode. So, was that diode something on the board? This is the direct way, and this is the reverse way. Let's see. Yes, yes. That diode was on the board, not on the IC itself. So, this mean this means that the MOSFET inside this IC is opened, is interrupted, has gone open, not short. I rarely find MOSFETs failing in this way, but it does explain why this track survived, why didn't the IC itself blow up, why didn't we see damage, smoke on the board. The MOSFET simply interrupted, and so did the current path in the flyback path. So of course the power supply could not work. So we have already found a problem, right? Nice. Again, me with my redundancy. Because as I said, as someone said, and I have pointed out in the last video, flyback failing in this unit seems to be a common issue. So I didn't make any assumptions, seeing the AC didn't blow up, and I went ahead to measure it because it takes a few seconds, right? And what do you know? We found a problem. I couldn't be sure if I hadn't received those spare parts from Tony, but I knew that any MOSFET does have a reverse body diode. It is part of the manufacturing process, so it can't miss. And since that higher that higher forward voltage seems unlikely, I knew I had to be sure. So yeah, let's get the new driver in. This is the new snubbing capacitor. It should read 10 nanofarads. So let's see. Come on. Yep, 0.01 microfarads, 10 nanofarads. Bang on. And this is the spare for the flyback driver. You need to put enough solder on the source pin because they drain the heat away from the chip. They dissipate it on this track and onto the board. Now the capacitor. As I feared, I damaged this cap. It is plastic. It is a plastic capacitor, and this track is quite large. The problem are the pads themselves. Look, they barely come out under the capacitor. So it is quite difficult to solder it, but I have to. And I am annoyed by the fact that this is a plastic capacitor. This is liquid flux. It works quite well with SMD parts. And that small brush makes it very easy to apply. I can't seem to be able to straighten it out. And I do not want to force the issue because I will damage this one also. And I do not want to do that. So let's see, do I have my 10 nanofarads on this resistor? Yes, I do. This capacitor is in parallel with this resistor because this resistor discharges the capacitor. So yes, as long as I have my 10 nanofarads on this resistor, I can ignore the fact that the capacitor is quite bended, quite on his side. No, I do not want to force the issue. It will get damaged, this one also. And I don't want to risk that. I think I am ready to test the auxiliary flyback supply. And because we need very little current on the mains, I'm using this light bulb, a 100 watts one, in series with mains, with the live wire, just to, if nothing else, then at least we protect those big fuses on the mains. So I have connected my multimeter straight on the VCC pin of the PFC controller, just like on the other supply, because that is where the 12 volts comes in, and also on the main capacitor ground, because this is a common ground point on all the board. So yeah, when I plug in the mains, I should see here on the multimeter 12 volts. I did remember to check the continuity between this capacitor's ground and the main filter cap's ground, and it is there. And also this Zener diode, because as I said in the last video, someone pointed out that in some cases this Zener diode gives up, and no, this one seems fine. So I think we are ready to test it. So in 3, 2, 1, go. Do I have my flyback? Yes, I do. 13 point what? 3 volts. The light bulb seems to light up a bit. Why is that? Where does the current go? Maybe that light bulb is small enough so it partially lights up. So I am using that 200 watts light bulb from the other video. Of course, I used my electric tape just to make sure I don't give myself a shock. And again, as I said, and I will always repeat it, never do this unless you are 100% sure of yourself. These are little voltages. You could die from this, so don't try it unless you know what you are doing. So let's see now. The relay clicked, and yes, this light bulb doesn't light up. So maybe relay coil flyback auxiliary supply and other stuff on the board draws enough power to partially light up that light bulb. So we have a working flyback supply. That's great. So indeed this damn thing was faulty. There are no shorts on the board because look, the flyback supply remains on long after I removed the power from mains. So no, nothing seems to be shorted on the board. So yeah, good news thus far. I have connected my bench power supply to my laptop via USB connection. It is a Raiden RD6024W power supply, programmable power supply, switch mode of course, and I'm using this interface. It is a dedicated desktop interface and it's quite nice. It lets you do just about anything with that power supply. Why did I connect it? Well, I want to test the fan. So I have set my power supply to 12 volts and 1 amp. And I did connected these leads to the fan. And when I activate the power supply, the fan should start. So now, yes, the fan started. And look here, I will remove this part of the interface and let only this side on the screen. So yes, the fan works. Just over 200 milliamps of current drawn by the fan. So the fan is okay. That is good news. The fan says that it should draw 300 milliamps and it draws a bit less. So yeah, it is okay. It would have been bad if it would have drawn more than 300 milliamps. Let me set up the microscope so you can take a look at this board, the fan board. I have set up my microscope. So as I said, we can take a look at this fan board. There seem to be a lot of unpopulated pads on this board, but we don't need to care about that. But check here. This is what seems to have gone bad on the board. Hey, where are you? I seem to have lost it. There we go, found it. I have lowered the microscope just to see better up close. Is that an A8F code? Do I need to open the other power supply to make sure of the SMD code on this one? Doesn't seem to be other Tony3 8F marked on this board. But this is what seems to be written on it. Yes, Tony did mark the part that fumigated. Now I remember him saying that. It seems to be what, a transistor. If it only has two connected pins, then it's a diode. I have reopened the working power supply just to take a look at the working fan board to be sure about that SMD code. Yes, this is the one. This is the damaged part on the smoked board, and as I said, 8F is written on it, and look, it counts here. So yeah, this is the one. So the replacement parts from TME has arrived. Mainly the driver, the gate driver, the non-inverting version. Non-inverting means that the output is in phase with the input. And they saw Tony3 MOSFET. This MOSFET is located on the faulty fan board. That Zener diode was limiting the voltage on this MOSFET's gate. I did measure that MOSFET and it seemed fine, but I did not want it to take any chance, so I ordered replacement MOSFET just to be sure. And two versions of Zener diode. Both of them should be 5.1 volts, SOT 23. I ordered two versions of them because I wanted to make sure that at least one of them has the correct pinout. From the datasheet, both of them should be okay, but as I said, I wanted to make sure. It is better to make sure than to regret. I will also have to replace the 15 volt Zener. You know, the one on the, this is from Tony. He sent this with the parcel, with the package, with the units. This is the Zener diode on the 12 volts auxiliary supply. You know the one that died on the Tony's video. And I will also need to replace the PFC controller IC. Tony asked me to do that no matter what the one on the board does, just to make sure. So yeah, we will get to do some soldering, and I will do it under the microscope just for the fun of it. But before that, I want to check something. So let's open the power supply again. I want to see, where does the fan get its power from exactly. It's on this connector, pins 1 and 3. Pin 1 seems to be the power supply, the plus side. Which, as far as I remember, it is in series with this MOSFET. Let's get the meter in the image. Yep. So I had a look around on the board, and as I have shown, the plus side on the fan connector is in series with this MOSFET, and the source of the MOSFET connects with this pin, and I have traced it back to this capacitor. So this tells me that the fan draws its power from the flyback auxiliary supply, and maybe, just maybe, this is why this controller fails, because as I have pointed out, it seems to be a common failing point on this power supply. Maybe on some conditions the fan, together with other stuff on the board, overloads this IC, and either with higher working temperature or higher voltage spikes on the snubber network, thus on the drain and the source of the MOSFET, causes it to fail. I'm not sure. I don't think it is an over temperature problem here, because there is no discoloration on the PCB, and also the controller has thermal protection, but there could be some dangerous voltage spikes across the drain and the source of the internal MOSFET in the controller. Or maybe some higher current spikes, which I doubt, because it is protected. But yeah, something is definitely causing this IC to fail. My money is on the voltage spikes across the MOSFET, and that can be tested with a differential probe. The best way is to test it with a differential probe on the oscilloscope, just because of the higher common mode rejection ratio. Tony has differential probe, and I will ask him to test it. But before that, as I said, I have to replace this Zener diode. This is the one that has failed, and it protects this MOSFET. So I need to replace that just to be sure. I will also replace this Zener diode, also 5.1 volts, the same with that one. It doesn't seem to be shorted, but just to be sure, because they are so cheap. Then this Zener diode, this is the 15 volts Zener diode. I will have to replace the gate driver and the controller for the PFC side. Then we can test if everything goes well. So yeah, let's get to work. As I said, this is the shorted Zener diode. Tony has marked it. And this is the MOSFET which it protects. So pin 1 should be its anode. This is a N-channel MOSFET. This is its gate, and this is its source. So this should be the anode of the Zener diode, and this the cathode. So pins 1 and 3. Yeah, or maybe I am messing them up. Anyway, let's desolder it. This is the 350 milliwatts Zener version, and it is a good thing I've ordered 10 of them because one just fell on the floor and I cannot find it. This should be its anode and this its cathode. And with the red wire on the anode, the red lead on the anode and the black on the cathode, we should see a normal diode. Hey, it doesn't seem to want to cooperate. But there we go. I am using my 0.5 millimeters leaded solder wire. These are the replacement MOSFETs, and as I said, I'm replacing this MOSFET just to be sure because that Zener diode could not have failed in any other way than with some overvoltage on it. And since it does protect the gate of this MOSFET, the MOSFET could also have been damaged in some way, and I want to make sure. Job done. This is the same 5.1 volt Zener diode as the one on the fan board. This is on the main board side, near the comparator. And as I said, I do not want to take any chances, so I will replace it. This pad seems to have been lifted, but it is not needed, so it's okay. This should be connected to here, which it is, and this here and here, which it is. So both used pads are okay. Let's make sure we do have a working diode here. So red test lead here, black test lead here, we should get a diode, and we do. Next, the gate driver, but first let's check something. As you remember, pins 1 and 8 should be connected together. They are not on the PCB, as you can see, but as far as I can remember, I have seen them connected together on the IC itself. So are they? Yes, they are. 0.5 ohms, and with shorted leads 0 point, so let's say 400 milliohms. This is why the PCB designer didn't connect them together. I guess this is. Looks okay. So now the Zener diode, which is this one. The diode was glued onto the board, which means the board was assembled by some wave soldering, I guess. Or maybe reflow, but my money is on the wave soldering process. This is the cathode side, so it is oriented okay. Yep, looks okay. The red lead here, the black lead here gives us a diode. Yes. And now last but not least, the PFC controller IC. And this one also is glued onto the board. And as you have seen in Tony's video, it is quite a struggle to unsolder it, to desolder it. I wonder, should I try with hot air? I don't think I should, because I would thermally stress the board due to that glue. Because I did not want it to risk damaging the pads, I chosen another way. I already have replacement controller IC, so I went ahead and dremeled out the pins from the IC itself. The tape is just to protect the board from flying debris. And all I have to do now is force out the glue. I think this is the safest way. Let me take out the tape. This is my tiny vacuum cleaner, portable one. I wanted to make sure I don't have any unwanted guests on the board. All the pins seems to have been dremeled out. This is a destructive way, but at least we do not risk damaging the pads. All I need to do now is heat it up a bit until the glue gives up. and it's already starting to move. But none of the pads move with it. Yes. I know it is not a very nice way of getting rid of an IC, but I think it's the safest way. All the pads look okay. It seemed to have left some solder in it, so I cleaned it up. And now the controller IC, the PFC controller, pin 1 here. All solder joints look okay. There aren't any solder bridges, so this should be it. I have cleaned up the yellow tape residue on the board, so now it's time to test it, because that's all that was needed to do. So we are ready to test. So I have my light bulb in series with the live wire of the mains. I have my multimeter connected across one of the output capacitors on the PFC. So when I connect mains to this ISC connector, if everything is okay, I should read here 390 volts or thereabouts. In 3, 2, 1. 392 volts. So yeah, we do have an working PFC. Yay, victory, right? I have removed mains from the socket and waited until the capacitors have discharged, because at first when I connected this cable, the light bulb seemed to flash a few times before the supply got settled. So let's try it again. 3, 2, 1. Indeed it does. It does flash a few times before it settles. Maybe it's due to the inrush current. which lowers the mains voltage. Due to the voltage drop on the light bulb. I removed the light bulb and connected the mains directly onto the board. It should be okay, but let's be sure. So 3, 2, 1, go. Yes. With the light bulb, the relay on the board clicked several times, but without the light bulb, the relay clicked just once. So yes, due to the inrush current, the voltage drop on the light bulb was too much. So at first is that cycle on off due to the under voltage protection. So yes, and thus far everything seems okay. I have just discharged the capacitors. I had just connected all the modules on the output, and I was planning to test if the fan board works. And as soon as I connected the mains, the same Zener diode on the fan board just smoked. Why is that? Since we do have a working main board, why does this Zener diode fails? It failed immediately. I want to test something. Because the replacement MOSFET is a plus minus 20 volts on its gate, I removed that failed Zener diode and I connected my multimeter across the gate and the source of that MOSFET, because that's where the Zener diode was connected. The red test lead on the gate and the black test lead on the gate, on the source. So this way I want to see what kind of voltage that Zener receives. What made it failed? I did connect the output modules as well, just in case the fan board needs them. So now in 3, 2, 1. 37 millivolts? Really? Then why on earth did it fail? I replaced the failed Zener diode with one of the other variant. So let's see, will it smoke again? In 3, 2, 1. No, no smoke. What on earth? Let's see if the Zener is okay. I should have my diode in this way. Yes. So it is not shorted. Yeah, you can see it's not damaged this time. So why did that one fail? What on earth? I honestly have no idea why. It is the same voltage diode, Zener diode, the same polarity, the same pinout, just a different one, a different code. Why is this one working, but that one is not? I have no idea. I did check under the microscope to make sure all the solder joints are okay. And this time, so everything seems okay. So why did this diode not fail? Well, I can think of only one thing. Maybe this is why. I'm not sure if you can see. This connector is not keyed, so it is quite easy to make a mistake, a slight mistake. See? In either ways, maybe I connected it slightly offset. I don't think so, but it could be. But then again, Tony did the same thing when he tested this board, this fan board. Is it possible that the both of us did the same mistake? I'm not sure, but it is not okay. It is not okay that this connector is not keyed. Just because you can easily make a mistake. So, this time I made sure it is connected okay, and I made a mark. I'm not sure if you can see, but the pins do line up. I made sure of this. I did clean up this one, this side of the connector. So now you cannot make a mistake. You see? The mark needs to be on that window. I'm not sure that this was the issue, but at least we have redundancy. I am ready to test the power supply again. I have mounted everything on the back side of the case just because I don't want to have stray connections on these connectors. I have my fan board connected the right way. Anyway, the the case does not let you connect it in any other way because it has that cuts. So I have my fan connected to the fan board. I have my global inhibit engaged. So all I need to do is connect the mains to this connector and see what happens. Do I have outputs? No. Does this mean that the global inhibit? Yes. Just like the other supply. It wasn't really connected. The fan works. No smoke from the fan board. Yeah. Yay, we have. But wait. 12 volts and 24. Yep, 23.97, 24. Yeah, victory. We have a working fan. So we have a working fan board. We have a working global inhibit function, just because you've seen that it didn't work at first, but when I moved it around, it started. We have outputs. So this is it, right? Yeah, this is it. Finally I can say that this unit is also fixed. So let's make sure the global inhibit works. What happens if I pull out this resistor? Yep, the fan stopped. And if I put it back again, yep, the fan started. Yeah. Yay, victory! All the screws are in place. I've made sure of that. Yep, here too. On the back side and on the other side. Yep, so this is it. I'm sorry if this one is a long video as well. I'm sure it will be. I have loads of video material. I will try to edit it so it won't be too boring, so it won't get you guys to fall asleep while watching it. But this is it. So this is the video. I'm happy I could help Tony with this one as well. So if you watched the video until the end, thank you very much. If you liked it, please subscribe. Do remember to subscribe and give it a big thumbs up, just to help me with the YouTube algorithm. If you like my work, you can become a member of my channel, or you can buy super thanks to support me. So this is it. Thanks for watching. I'll see you next time. Bye.